Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
We made it.
Hi.
We made it. Even though the backgrounds blend in pretty seamlessly, like, ready?
Sort of.
You think my fingers, it's not going to disappear. Oh.
Yeah.
Just like.
I'm making our hands kind of match.
Make it look like we have
bit.
the weirdest looking hand. Yeah, that would be really cool.
There we go.
Oh,
2 double thumbs. Let's go.
I don't know why that's so fun. That's like when the lights go out and you start making like finger puppets on the wall. It's like endlessly entertaining no matter how old you are.
Yes.
Well, we are in different locations because Alex has contracted the bubonic plague. You thought that it was gone in the, oh gosh, I'm going to make my knowledge of history really terrible. 1200s? 1600s? Something hundreds. The bubonic plague.
It was a while ago.
Killed a lot of people.
Definitely in the hundreds of years.
More than 10 years ago. Anyway, you've got it.
I got
so
something.
That's why you're not.
And I am out. It is. I've been describing it to Neil. Waking up each morning is like a phlegm pinata.
You said that, and the first thing that I thought was that that's a great name for like a heavy metal rock band
from like the early 2000s.
Can you imagine? Yeah, exactly. Like, you know, I'm trying to think of examples, but just that's when, you know, all the like Jimmy Eat World. I know it's not a heavy metal band, but just all these weird names. There's probably stories for each of them. Yeah. But I just remember all these names, and it's just like, yeah, we're Phlegm Pinata. We're gonna be rocking out with you for the next 2 hours. It's such a great band.
It's a great band name.
Especially because no one knows how to spell phlegm.
Yeah.
It's a very strange.
I was like, let's see, F-L-E-M. Nope. Hold on. Let me Google that.
This would be like one of those Ryan George sketches where there's like the department of people who name things, and they're like, you know, let's throw a G in there, but there's no sound. No, I think we should throw a G in there. Oh, I don't know if that makes any sense. We're gonna do it anyway. Exactly. Chipmunks get the black plague.
Really?
Did you get the black plague from chipmunk?
Oh my god.
I mean, you should. That's not a good thing to have as a pet, Alex. Chipmunks are not good pets. That's why you're getting the black plague or the bubonic plague. Is there a difference between the black plague and the bubonic plague? Is that just the same name, or is it a different thing?
You know, this isn't electrochemistry live stream. We're asking some serious history questions.
Every week I change the name from like ask us anything about the stock market or ask us anything about the bubonic plague. You know, it just gets better. Well, anyway, we are back in separate locations, but it's been a while, and there may be a few more weeks yet, at least in this month, where there's an ACS conference, there's another couple of workshops, excuse me, and basically the entire first 2 to possibly 3 weeks of September I will be gone, so,
just happens for us.
So we'll make these happen. We might do another random one on a Monday if we can. We'll make these live streams happen as often as we are around, able, and not currently a phlegm pinata. So we'll do the best we can. But let's get right into it.
We have some questions.
Ron has a question. Ron says, explain negative and positive current. How do we calculate CV of a 2-electrode system? What does negative voltage, negative current, positive voltage, positive current mean in CV? Okay. Well, at the risk of sending something to you with your broken vocal cords and stuff, this is kind of your you have a lot of slides I can do it.
Either way is fine. I can you know what? Let me get. I have a. Let me get a file. Let me get Let me just get a slide.
So the short answer, while Alex is finding stuff, Ron, is that all of this is convention, basically. Potential a little less so, but current. The short answer to your question about current is that it's the direction. So positive and negative current simply indicates the direction that the current is flowing. But I'll let Alex.
Yeah. So all I have here is these are just plotting conventions for cyclic voltammograms, and Neil's right. A lot of it has to do with whatever the convention may be. So I'll just start inking because that's what we do here. There are two conventions. I'm going to start with probably the more common one, which is the IUPAC convention, International Union for Pure and Applied Chemistry. And so in this case, positive potentials, high potentials are on the right, low potentials are on the left. And then when the current is negative in particular, so when this is a negative number, it corresponds to a reduction reaction, which is to say that an electron is moving from your conductive electrode to a molecule in solution. With my illness has also gone my drawing abilities. Not that it was any good, but this is reduction. And then when the current is positive, it's the opposite. So in this case, the molecule is going from the electron is going from the molecule to the electrode. So physically, that is what oxidation and reduction are: negative current and positive current. So positive current, oxidation, electron moves from molecule to electrode, and then reduction or negative current is when the electron goes from the electrode to the molecule. That is under the IUPAC convention. The US convention, or sometimes called the Texas convention, is a bit different. It flips it, basically. It does a whole, I think it was like a symmetry operation like S or something like that. But basically in this one, negative potentials are on the right-hand side, positive potentials are on the left, and then a negative current corresponds to an oxidation reaction, and the positive current corresponds to a reduction reaction. So it's not enough to simply say, oh, these things are just like, you flip this thing around. Like, you can literally get these two things by taking this CV and then just going like this, just kind of changing its orientation. Like, see how this arrow is pointing this way? If I just turned it all the way over, then it would kind of look like, oh, now it's going the right way. See, like, the reduction would go to the top and the oxidation would go to the negative. And it would be cool if that was just it, but the sign has to change. So you also have to negate the values on the current so that you move between US and IUPAC convention. So that's what they mean. That's what it is. And I don't know if he has any further clarification.
Well, there's a follow-up thing.
There's a follow-up?
Well, there's a follow-up question, but I'll kind of clarify, because I think the way that he's worded it is not. You have to be careful. So, well, first of all, the end of this was also just about what does negative and positive voltage basically mean. So you explained the CV convention. All I was going to add to that was that on a fundamental level, outside of CV specifically, recognize the fundamentals of electrochemistry in general. So this is CV, this is chronoamperometry, this is anything. This is just electrochemistry fundamentally, okay? So in electrochemistry, if I have some redox reaction, A plus an electron goes to B, we write this as reduction, right? So the electron is being added. It's on the reactant side, if you will. This has some E0 value, some E, value. So this is, I guess I should use numbers just to make it easier. So if I do like 0 volts, right? Then if the applied potential E applied is greater than E0, then the oxidation will happen. If the applied potential is less than E0, the reduction will occur. Okay, so reduction, if E is less than E0, this direction happens. That's the reduction, right? This is the reduction for E is less than E0. It means you're going to force this reaction to occur that way. If you have a greater potential, then it's going to go the other direction. You're going to push it. So the only main point that I want to make here, again, whether it has anything to do with CV or not, is that just in an electrochemistry framework, sort of fundamental of electrochemistry here, don't think about this as necessarily positive or negative, but more positive and negative of the standard potential that you're studying. That's what's more important. Now, in this case, I picked 0, like just to be a very easy value. So in this case, it would be actually positive, like above 0 or less than 0. But if my E0 was 1 volt, then a positive potential of 0.5 volts would be negative of the standard potential. It would be less than the standard potential, even though it's a positive number. It's relative, right? It's relative to whatever the E0 is. That's what's most important when you're studying redox reactions, which is what electrochemistry is. So keep in mind that part of it, which is to say, in a vacuum, just by itself with no other context, when you say, what does negative potential mean? What does positive potential mean, or voltage? Nothing. It's all with respect. It's like, it's relative to what? With respect to, versus NHE, SHE, is it positive or negative of a standard potential? All of it's the relativity of your voltage, your potential is what matters much of the time. So I just wanted to make that point clear as well. So the current, in other words, is the direction that the electrons are flowing, and the potential or the voltage is relative to something else. So electrochemistry can be tricky that way, because there's not a lot of like absolutes, like, oh, if you have 0.5 volts, that always means something. It's like, not necessarily. It means, what is it with respect to, how positive or negative. 0.5 volts could be a strong oxidizing potential for something. It could be a strong reducing potential for another thing. So you got to be careful what you're looking for there. And then just the last point on this, sort of be careful with the naming and the nomenclature, is your second question. Direction of electron flow from cathode to anode is taken positive for IUPAC. Maybe. What are you studying?
Yeah.
So the anode and the cathode, how they're connected might be slightly different if you're working on a battery, if you're working on a fuel cell, if you're working on an electrolyzer. We use these terms anode and cathode, but they are a little bit tricky depending on what you are studying. So for instance, if this is a battery, typically in a battery, the cathode is what we would connect to, like the working electrode, so to speak, which is to say that the battery or a fuel cell is the same, is a device that like delivers energy, sometimes stores energy, but we can think about it as an energy delivering device. The cathode is then by definition the electrode, where when it's delivering energy, the reduction's happening. The anode is the electrode in a device like this. This is a somewhat narrow definition, just to be clear. This isn't like, if it's an electrolyzer, the things kind of go backwards. They're actually in the reverse. But again, in an energy delivering device like a fuel cell or a battery, the anode is the electrode where the oxidation is happening when it's delivering you power or energy. So in that particular case, if the direction of the electron flow is from cathode to anode, that means that the electrons are going to the anode. The anode is reducing. And the cathode is oxidizing. Yes, it's a positive current. That would be a positive current in the IUPAC standard, because that's like charging a battery. It's associated with a positive current. And so the negative current would be associated. This trips people up all the time. When you're studying a battery with like a potentiostat and you have a negative current, that's the discharge. If you've connected it, sort of ideally, it'll have a positive voltage and a negative current when it's discharging. But again, I'm not going to dwell on this anymore, because just be careful, because it depends on the convention. It depends on exactly what you're studying. Battery, fuel cell, electrolyzer. With an electrolyzer, a lot of times it's the opposite. The anode is the one that's sort of the working electrode, and then things are flipped. So it's a little tricky. And so I just wanted to kind of maybe talk through some of that. Try to move on now. We could talk endlessly about convention. It's one of the things about makes electrochemistry really frustrating for new people, I think, because it's like, how do you talk about everything and clarify what you mean when another person could have it exactly opposite, right? Yeah. So you're talking about a battery. So then what I said was probably accurate for you. So yes, reduction happening at the anode of a battery is a positive current in the IUPAC convention, and it's a charging mechanism. So,
okay. All right.
It looks like this is an exam question, and you know how I feel about exam questions.
I know how I feel about exam questions.
So Shrews BG, I appreciate it, honestly. So this question is for Sal. This is clearly lifted from either the G exam in India or a test in a class of some sort. Like, it's, you know, I find myself having a hard time explaining why this isn't exactly the right place for this. Like, we're not here to answer homework questions and do your homework. It's not really what we're trying to accomplish with this live stream. This is like, this is not, at least in my opinion. I don't know if you want to add anything to this.
I mean, like, I'd say if we have time, we can look at it. I always find, I just like solving problems just in general, but and also we don't want to, most of the time the questions that we get they're research related questions, and we also don't want to, and it's like with the research, it's a little bit more vague sometimes, and we also don't want to like tell you how to solve something and it ends up being wrong, especially because most of the time if like in your question here, it's like calculate the cell potential.
I mean, it's probably pretty simple, like delta G is NFE, and you just got to use the Nernst equation.
Some stuff like that. But then also, if you're actually a scientist trying to calculate the cell potential, you'd use a multimeter or a potentiostat and just measure the open circuit potential. So that's what we would tell people to do.
Right. Yeah, and I think your first point is another reason that I don't like these kinds of questions, and so I'm sorry to kind of let you down a little bit here, but it's like, at a quick glance, again, it's like you have the delta G, you have the solubility product. Delta G is NFE, and E is defined by the Nernst equation, and it's probably manipulating those two expressions, but like there's a good chance that I'd make some dumb mistake if I tried to start solving it, and it's like, that's another thing, is just from honestly a quality of this live stream and video perspective, either Alex or I kind of writing through and solving, on the fly, and then being like, plugging in numbers and maybe accidentally making a mistake. Like, it's not necessarily going to help you, because if we do it wrong or we forget, or we're just like, I forgot. Like it's been the other thing, it's a research sort of minded with these kinds of questions that we like to try to talk about. And some of this kind of pedagogical stuff, frankly, it's been a while, and like I would want to like just look at a textbook really quickly. Like I want to go open one of my like thermodynamics or something textbooks and be like, oh, that's right. Just before I do something really dumb, because it's been a while since I've solved like school level problems, to be honest. And so I don't want to lead you astray basically and do something dumb while sort of under pressure of a live stream here, frankly. So
and I'll just say, like, I think Neil's also right. It's like there's a delta G equals NFE or minus NFE. There's also probably in this a Nernst equation related thing, because you have some concentrations, solubility products. That's also another thing related to solving these problems. But you don't have the time to go through.
Rebecca is here, and you're never going to believe it. She has an impedance field question. It's very unusual. Yeah, Rebecca, you should mix it up sometime. She says the error parameter when it is more than 100%, does that mean the component is overfitting the system and should be removed, or the value is just inaccurate? It doesn't mean the value is inaccurate, but it does. Actually, I shouldn't say that. It could mean the value is inaccurate, or at the very least, it just means statistically that the way that I think of it is this value can change a lot and it doesn't affect the accuracy. So you can interpret that one of two ways. One is that this set of values of the solution is perhaps a local minima and not a global minimum. It's not the best possible solution, because if one of the resistors or capacitors or whatever can quite literally be doubled, 10x, halved, 0.1x multiplied, you can just, if you're using like our software, you can use the slider bar back and forth all over the place, and it doesn't change what everything looks like. It doesn't change the fit at all. Then what good is that parameter? Why even bother having it? Right? So one possibility is to say, I should just remove this resistor or this capacitor from my circuit entirely, because what good is it doing if its value can be literally anything and it doesn't change how the fit works or looks? Then it's pointless, right? I mean, that's one way to look at it. The other is that if you say to yourself, well, I can't get rid of that. I know that thing matters. I know that that's a charge transfer resistance from my process or something, right? Then you may have to manipulate the values such that the algorithm finds a better solution somehow. Now because the I've talked about this in like my circuit fitting webinar. It's like the algorithm is just trying to minimize everything and get the best set of error solution, whatever, that it can mathematically, but it doesn't know that that's the best possible solution. So you might have to force it. And this happens a lot when you have like slight features. Like sometimes there's like a slight semicircle and it's like the software just doesn't want to like fit that resistor quite well. There's times where that happens. And it's like, what I'll find myself doing is like locking in 2 or 3 like RCs or something. Like I'll lock the Q and the R and force it to stay there and then like fit the other stuff. And I'm just refusing to let it fit these parameters, because if I do, it will like minimize the resistor, it'll maximize the capacitor, or vice versa. And it'll just do what you're talking about, where it's like, it will essentially be irrelevant. And I know, based on my knowledge of my system, that element is not irrelevant, right? Sometimes the answer can be helpful by telling you that a circuit element is irrelevant because you're not sure what the circuit should be, which that's fine. If the mathematics, the algorithm kind of informs you, this is not relevant, great. Then I can change my circuit. I'm getting information. But if I'm at the point where I do know with relative certainty what my circuit analog should be, then by finding that the values reach these pointless values, so to speak, I'm instead going to interpret that as I should try to manipulate my fit to make it better. Because what good is this resistor that I know should be here if its value could be literally anything from 10 ohms to 10 mega ohms, and it makes no difference? So what I'm going to report a value, and that means that's supposed to mean something. Obviously it won't, right? So so I hope that kind of gives you the two, ways to interpret when that happens. And then, is a really small error also unreasonable, like a value of kiloohms, an error of nanoohms. I mean, I don't know, the elephant in the room is that your fit is fantastic. Like, it's possible that you just have a really, really good tight fit. This could be a situation where you have the opposite situation of what I just described, which is that if that value changes even in a minuscule way, the fit will be terrible. And so it's very accurate. That's how I would interpret that. I mean, I think, I mean, it seems like that's what you've obtained, I suppose. That's pretty rare in my experience. I think the biggest discrepancy that I usually will find, and like the best kind of fit you'll see between the value and its associated error is like I would say like 2 to 3 orders of, like 3 orders of magnitude. So you might have like an ohm, with a milliohm of error. That would be probably the most that I usually see. But if you're talking kiloohms to nanoohms, that's like 10 to the 12 difference. I mean, that's bizarre, honestly. It could just mean you have the most accurate fit in the history of mankind, which maybe that's what you did. Otherwise, I'm honestly not quite sure how to interpret that. That's a bit bizarre. I guess she continues here. I'll just do this. Totally answers your follow-up question, but yeah, maybe that was the follow-up question. But in fitting, I can change parameters sometimes a lot, and it gets similar fit. Yeah, okay, so that was what I had said before. EIS really seems to be a black box without other tests. Yeah, well, EIS is a black box. That's why we all love it so much, because it's we're just constantly. I think for me, the thing that's the most frustrating about impedance is similar to the TAFL analysis that I talk about, where I'm like, you can use the TAFL slope to inform where the kinetic region is, or you can pick the kinetic region to get you the TAFL slope. It's like it goes both directions. And then it's like, well, which one's the correct? And so, in other words, the impedance can be a thing where your fit infers what the circuit should be and what's going on. And then sometimes what's going on and what the circuit should be, and that informs the fit. And it's like, how can both of those be true? Like, they can't both be true, but somehow you sort of do both sometimes, where you like justify which circuit to apply because the fit does work quite well, and there is a logical, like, phenomenological explanation. And sometimes it's the exact opposite. So it's a pain in the butt. Just stop doing impedance, stop doing electrochemistry altogether, do something else.
So is whenever our answer is stop doing electrochemistry, it's it's rough.
Yes, it is. Ask us anything about electrochemistry. Okay, the thing I'm telling you about electrochemistry is stop doing it. So yeah, it's tricky. So I hope that's helpful, Rebecca.
All right. Next question, kind of going back up. When conducting chronoamperometry or chronopotentiometry, is it possible to determine which part of the response is due to the relevant electrochemical reaction, or if it's due to side reactions? I'm going to say no, just generally. So I'll just kind of share, let's see. So usually whenever you are doing like chronoamperometry or chronopotentiometry, you get responses that tend to look like this. So if it's time and this is current, you have your initial like spike in current, and then there's like a decay. And sometimes it changes or trails off. And then in chronopotentiometry, you kind of have a similar response. Maybe it kind of goes like this, and then it just kind of changes like that. So normally, the only real power that you have in determining whether side reactions are occurring is your control of your current or your potential. What these two things are in your chronoamperometry and your chronopotentiometry, respectively, sort of say. So if you choose a potential where it's thermodynamically possible for many reactions to occur, then the total current is going to be a combination of all these things. And there's nothing in particular about like, oh, we know a couple things about like, oh, the area like here at fast time scales is due to some things, and then at slow time scales is due to other things. Although you're talking about bulk electrolysis, I think in general, so we can't actually use this. But these potentials and currents don't tell you too much. The only thing is in chronopotentiometry, whenever you see something like this, where there's like the potential either has to go up or down to maintain the desired current, that usually indicates that another reaction is happening, right? Another reaction. You've completely used up or consumed one reactant, and so now the potentiostat is choosing a higher voltage to make sure we can get 10 milliamps, 1 milliamp, however much current you want driven through the system. So that's the only thing you can do here. That's what you can do to tell that this is particularly happening. Maybe you can get some similar changes when like you see the current start to change or kind of go up or go down more. The potentiostat is doing something to get constant current, constant potential, but generally speaking, no, you can't tell like hydrogen evolution's happening here and CO2 reduction's happening here or something like that. So that's my 2 cents about if there's other side reactions occurring. Usually people might use another technique like a rotating disk, or rotating ring disk in particular, to detect if there's a side reaction occurring during an electrolysis process.
Yeah, but that's usually like a voltammetry kind of a technique.
Correct.
Too. So yeah, as a general rule, chronoamperometry and chronopotentiometry are, as you said, sort of definitionally susceptible to side reaction kind of convolution of the data. It can be hard if that's happening to get perfectly accurate data all the time. So okay, so it looks like again it's a little.
Nope.
Oh, sorry. We're fighting over unlocking the door.
You go for it.
No, I'm done.
Okay, I'll click it.
Another little EMF of the cell. We're going to kind of move on here. Goran Toma Cruz says, when measuring electrocatalytic performance using rotating disc electrodes, is there a direct correlation with evaluating performance with MEAs, membrane-electrode assemblies, or are there assumptions to look out for? This is a great question.
Good question.
So honestly, the answer is yes and no. The answer is absolutely yes, from the perspective that we wouldn't be doing rotating disc electrode experiments as a method for electrocatalytic performance if it wasn't helpful when it comes to MEAs and full cell fabrications, right? If that wasn't the case, there'd be really no point in doing the RDE tests. So yes, there are for sure. But if I'm gonna be honest about direct correlation, not always. I guess the reasons are that the transport phenomena, the fundamental electrode interfaces are different when you compare RDEs and MEAs. So for example, in an RDE, I'm looking at a planar disc electrode. So my hand is like out of camera when I normally do. It's over here in front of my face, right? So you have a planar disc electrode with solution under it, and the disc is spinning, and there's a solution being forced into it. It's a solid liquid interface, very well controllable kind of a thing, and you get kinetic and mass transport information, basically, like you said, the electrocatalytic performance of some material. When you make an MEA, if you're looking at a fuel cell or an electrolyzer, for instance, one of the first fundamental differences is that you might have sort of a electrolyte soaked membrane. And so there is kind of a solid liquid interface, but you also often have a gas diffusion layer with your catalyst, and you have a sort of a solid gas interface now. Whereas with the RDE, you might have, like, for example, dissolved oxygen if you're studying oxygen reduction reaction or something like that. Whereas now you have oxygen gas or air flowing onto a gas diffusion layer to interface. And so the transport phenomena, the interface is a little different. The amount of oxygen even present might be different, because oxygen, frankly, we this is just one example. It could be other, gases or other materials, but and some MEAs in cells are liquid phase too, to be fair. But just as an example, you just talk about different assumptions and things like that. Oxygen doesn't dissolve in water all that well, to be honest. So one of the tricky things is that, the assumption, we're making the assumption, for instance, that the smaller, I suppose you'd say, more controlled amount of oxygen in the RDE system that we can, know is based on the saturation, amount of oxygen at whatever temperature in solution, is going to be applicable or the same level of performance with a gas diffusion layer and a channel of humidified oxygen where there's a lot more of it in a gas phase system. So yeah, so that's some of the assumption we're making, is that it will behave and perform similarly. Now, what hopefully will happen, I would say, I can't even say does necessarily happen, but is that you study the electrocatalytic performance with your RDE to, observe and calculate kinetic, quantifiable kinetic information, for instance, about the electrocatalyst you're studying. And then when you construct MEAs with it, the good catalyst versus the bad catalyst or whatever, that performance tracks into the MEA, so that, like, you don't suddenly get, like, the worst RDE catalyst suddenly performs really well in the MEA and you're wondering why, right? I mean, I don't think most of the time that does happen. You only might be in a situation where the RDE is a good screening of a lot of different catalysts, and then you only want to make MEAs with the ones that perform the best. And then as far as direct correlation, it's like, well, now the MEA is for really testing the real system, so to speak, in a full setup, and test its longevity, test how long it actually works before getting poisoned or deactivating or something like that. So that part of it there, the direct correlation, because it's just a slightly different system, the interface is a little different, the transport phenomena, the lengths of transport are different, through a membrane as opposed to a well-controlled diffusion layer thickness when you're rotating the disk. Some of those things aren't exactly the same. So that's where there's assumptions that the performance will translate to the MEA have to come into play. So no, not precisely a direct correlation, but there's definitely a correlation and, predictive power, I would say, in the RDE as it relates to the MEA when you start constructing those full cells. I hope that's clear. I know I kind of talked through a lot of stuff there, but anyway, that's a somewhat comprehensive answer for you there. So
nice.
There was a follow-up question, looks like, about the CA and the CP.
Yeah.
I just wanted to catch this because it says a follow-up question here. You can cross-check potentials for CA definitely, but how about for chronopotentiometry?
I think so. I think it's like you can use a multimeter and hook it up to your electrodes for CA, and it's like great. You told the potentiostat apply +1 volt, and then the multimeter reads +1 volt. Good match. In CP, you're measuring current, so it's a little bit different. You can still use a voltmeter to
Wait, do you mean the opposite there? CP, you're measuring potential and you're controlling.
Correct. So I think then the question is, like, how do you know that the right amount of current is being? That's how I guess I'm thinking about the question. How do you know that 1 milliamp or 10 milliamps is what you're applying?
Oh, I took his question as cross-checking potentials for CP as well. Unless he means cross-checking the current. Like, in other words, does he mean cross-check potentials for CA and cross-check current for CP? Or cross-check potentials for both.
Cross-check potentials for both.
Do you know what I mean? Like, you're taking it as the control variable, and I was just taking it as potential.
Yeah.
So I don't know exactly what he means by his question.
Yeah.
Because you could use a multimeter
you could do
for both.
Yeah, exactly. Yeah, you could do it for both.
Right. It's just that one of them, the potential is changing all the time.
Yeah. One of them, the potential is changing. The other one, the potential, you would, well, in the one that's changing, you'd like kind of watch both of them. It's like, all right, is it approximately the same? Kind of looking back and forth if it's changing. So, but yeah, if he was wondering if there was a way to cross-check whether or not the right amount of current is flowing, then you may need like an ammeter or something like that. So I don't know if that's exactly what he was asking for, but yeah, I would say definitely put a multimeter. Digital multimeters are very valuable to have for doing electrochemistry, in addition to a potentiostat. He has another question immediately next. Usually recommended reference electrodes for alkaline media is mercury oxide, but there are safety risks here. Would switching with an RHE or silver chloride suffice? So generally speaking, I think Neil, you know a lot more about this, but like unless the alkaline media is really low concentration, like low concentration potassium hydroxide or something like that,
or like carbonate,
or carbonate,
mildly alkaline,
then you can use it without issues. But but generally speaking, you'll get like glass will start to dissolve in alkaline.
And Chris pointed out the same. Silver chloride can have compatibility issues depending on the species involved, exact conditions. Yeah, my take on this is honestly, it's exactly as you said. I have sort of a different feeling, but it's mainly because in my research when I was in grad school, I did a lot of alkaline electrolyte stuff, but it was low concentration KOH, carbonates, and bicarbonates. And so we're talking pH from like, let's just say like 10 and a half until 12 and a half to 13. Not 1 molar KOH, which is like 14, like soup, just at some point we sort of stop talking about the pH when it's like, it's like when you have 1 molar HCl, if you do the math, it's like less than 1, right? It's like, and you have 1 molar KOH, it's like 14. It's maxed. Yeah. Like it's all the way. It's all the way up, right? So when you have a really strong alkaline solution like that, no, it's just not a good idea to use. Basically, first of all, any glass-based electrode is generally to be avoided. It's just not a good idea. And then there's other kinds of possible contamination things or instabilities that can happen with, alkaline into like other redox couples. Again, that being said, if you have low strength alkaline, I used calomel for most of my tests and it worked just fine, but it wasn't terribly strong alkaline. Your other option is to use a salt bridge. So you can use silver chloride as long as you have like the silver chloride is sitting somewhere away and you have a salt bridge maybe with a frit or something that has not, maybe an intermediate solution. So you could have like 1 molar KOH in your main solution and then a tube with a frit at the end of it with like 0.05 molar KOH. So like very low concentration alkaline connecting to a separate like cylinder and your silver chloride in there, or maybe like KNO3 in there or something, but just not super strong alkaline. And so the reference electrode itself is not exposed to the strong alkaline, but you can still use it because if there's a safety issue with this mercury oxide, then that would be the way to kind of get around that, not having direct contact. So that's my other answer.
All right. And this chapter topic be done in a day? No.
Which chapter?
No. I'm just gonna say no.
No, but
whatever the chapter topic is, takes more than a day.
Which chapter or topic though,
I'm not so sure.
What if it's the chapter about the bubonic plague? I bet I could do that.
Maybe you could do that today. Can you tell about Nernst equation?
It's like they knew you were going to be here.
I know.
It's your
even
this next question. Someone just said
Nernst equation. I think they just know. I think people just know.
They just know you're here.
Just know I'm here.
They're just trying to make this. I just want to say, everyone, folks, we thank you, LX Stylish Gamers and Shush Unreal. This is Alex's favorite equation, and he's under the weather, so you're just making him feel better, and we appreciate you.
Yeah.
I appreciate you. I just want you to know that.
So this is the Nernst equation. I'll just keep talking about. Actually, no. This is the word Nernst equation. That is the word. That's the word Nernst equation. This is the Nernst equation itself, and the Nernst equation relates to this reaction where you have an oxidized species A or something plus an electron goes to a reduced species, and basically, this equation just states that the potential of an electrode, the electrode potential, is equal to the standard react potential of this reaction minus RT over NF, the gas constant, the temperature, divided by the number of electrons transferred. In this case, it's 1. And then various constant times the natural log of the activity of the reduced species and the activity of the oxidized species divided by the 2. Sometimes we change these to concentration because it's a little bit just more convenient. But I find this equation to be very useful and powerful because, an electrode's just kind of like a metal or something in solution, right? Something it's in solution, and it has some number of electrons in it, if you will, like a Fermi level, and the energy and its potential will move up and down based on how many oxidized or reduced molecules are in solution. And so I can add more OX into the solution, change this ratio, and I shift the potential. But I could also use a potentiostat and a power source to also make these adjustments, and I can flip the ratio of what's near the electrode surface at the interface to reflect this ratio. So that's kind of the thing I really enjoy about this, is it really works both ways. For a long time I was just like, oh, CV just has the ability to we can change, we use an external power source to change the potential of the electrode and change the concentration of species. But you can do the other thing. You could do the opposite. You can change the potential by changing the concentration of these species. So that's something I really like about the Nernst equation. How it's very it works both ways. And for the longest time I thought it just worked one way. And yeah, so that's the Nernst equation. That's all I'm talking about, the Nernst equation. I'm not going to go on into a bigger tangent.
That's it. You're not going to talk more.
I mean, those are the highlights, really. I could derive it. Not going to derive it.
No. That's even that. I mean, that's
a bit much, right?
It would make you very happy because it's your favorite thing. That's good. Ron has a good battery question I can talk about here. So. And there's a follow-up a little bit below. I'll grab it in just a second. So he says, I did a CV of LFP versus lithium. So the lithium iron phosphate cathode, since positive electrode potential, and lithium is the negative, right? So the lithium was your sort of ideal, you'd say ideal anode there. Now I perform CV on it. The positive voltage I get from the CV is the potential of LFP while charging. Positive voltage. So yes, that's correct. I'll talk through it in a second. And the peak current and peak voltages for the LFP lithium system correspond to reduction and oxidation of the electrolyte and the current and potential. I should make sure there's no other follow-ups of this specific question. There's a few other things. So to your first part, the answer is yes. I'll just draw it a little bit of it real quick and talk through it, but I won't take too long. I see we have a lot of questions, so I don't want to take too long. I'll just try to answer your question pretty rapidly. I know I'm not good at that, but what I'm gonna do is I'm gonna write that LFP lithium iron phosphate reaction as an oxidation. FePO4. Goes to Li plus electron plus Fe PO4. So this is, I'm pretty sure that's the reaction is something like this. I might have it slightly off, but it's something like this. So this is the charge this way, and then the other direction is the discharge. Okay, so the oxidation is the charge. So to answer your question, essentially you said yes. So if you're looking at the CV, voltage and current, and this is, voltage versus Li plus. It's something like, it goes from about 3 to like 4 or 4.5 or something. I don't know. The exact voltages are iffy. And I don't know 100% where the peaks exactly show up, but if this is a zero current, when you're scanning positively, you'll get a peak somewhere here, something like that. Usually scan really slowly, and then when you scan backwards, you get the reduction peak somewhere around here. Again, it's like 3 or 3.5, or it's somewhere around here. This is the charge reaction. Positive potential, again, it's somewhere around 3.5 to 4 volts, something like that. That is where you are basically delithiating, if you will, the LFP cathode. And this peak down here is the discharge, which is where you are reducing the reduction reaction. You are lithiating the LFP, basically. I think that answers your question. You're just kind of asking about the charge and the signs and what corresponds to what. So that is correct. What it seems like what you were asking is correct. So if you need a follow-up, let me know. But that is what the CV probably looks like roughly for the LFP, and the which of these reactions is the charge discharge and which is positive negative, basically. So this would be positive current, that's negative current. So there you go. We'll move on again. I know because we have a lot of questions, but anyway, it looks like the next one's more battery stuff, because it's always battery stuff.
Yeah.
Gouy Majayan says, how to calculate the current applied for GCD analysis of coin cell batteries if I don't know the reaction happening and the theoretical specific capacity? Great question. So my advice to you is you're going to want to do a well, first of all, the answer is you're going to have to guess. Okay. Whether, no matter what, you're going to have to guess. So what you should do is assume, based on the size of the system you're studying. So it's a coin cell, so it's probably in the microamps to milliamps at most, if you're looking for a moderately slow C rate. Start slow just to be safe. You don't want to do like an amp and all of a sudden the voltage just goes insane, right? The one thing hopefully you do know, even if you don't know the exact reaction or the theoretical capacity, you should hopefully have an idea about what the voltage limits should be, or at least have a decent idea where they ought to be, like 4, 4.5, 3, 2.5, 2.8. You should have some rough idea. So what you're going to want to do is start with your battery cycler, your potentiostat, whatever, and apply. You're going to have to make up a current. Just make it up. 10 microamps. Pick something, right? Pick something kind of small, kind of safe, and pick a voltage cutoff, whether you're going up or down, or both, right? If you know it's 4.5 and 3 are your limits, whatever, right? Pick 10 microamps, and then what you're doing is you're just going to watch it. This is the crappy part. You're going to have to stare at the screen for a while. watch it and see, because it might shoot up immediately. It might take an agonizingly long time, in which case you'll have to stop it and be like, okay, I need more current than that. Like, it's not going anywhere. Or that's way too much current. I gotta pull back. But what you're going to do is you're going to find a current that hopefully takes like a reasonable amount of time, which for a battery is like 1 to 2 hours, right? Because you're looking for like, you're trying to find, I don't know, like 1C or 2C or something like that, right? And if you get a reasonable looking curve that takes 1 hour, well, then you have just discovered 1C. But you again, because you don't know what the capacity or the mass or any of the stuff with your system is, you have to find it experimentally. And so the only way to do that is to guess a current and look for where the voltage shoots up, and pick your upper threshold. If you're not sure exactly what that upper voltage is, give it like maybe it should be 4.2, and you give your upper window of 4.5. And so the voltage, you're applying a milliamp or whatever, and eventually the voltage just it shoots up, and then you cancel your experiment because you don't want to overcharge it or damage it. But you're going to watch for where the voltage clearly kind of, it's done plateauing, it's done intercalating, deintercalating the material. Look for that, and then figure out how much time it was. How much time did it take? Well, that one took 37 minutes. Okay. 37 minutes, however many seconds that is, multiplied by how much current, that's how many milliamp hours or how many coulombs, whatever the unit you're using is. That's what your capacity was, or your charge, right? So then you're gonna calculate experimentally the theoretical, the capacity, and then you can work out. Well, hopefully how many grams of your thing are there. You don't know what the reaction is yet. Okay, fine. And maybe you can work out those details later, but at least you can practically know that if I apply a milliamp, it'll take an hour. So in theory, if I apply 2 milliamps, it should take 30 minutes. Like, you're gonna discover, like, experimentally what these are. And so this is the part of battery testing that's hard, because most battery testing is like, set the cell to cycle 1 million times, and then you walk away and you go get dessert and come back in 2 months and your tests are done. In this case, when you're doing what you've described, you have to sit there at the computer and the battery tester and watch it, because you don't know. You might have picked way too fast a scan rate, way too slow. You're going to have to do some trial and error and figure it out.
All right. This next question, a little, don't know if I have a great answer. Highly theoretical and technical. In a highly concentrated water and salt electrolyte, the classical Gouy Chapman Stern model of the electric double layer breaks down entirely. Instead of a monotonic decay of potential, X-ray scattering and simulations reveal an over-screening effect, resulting in an oscillatory potential profile near the electrode surface. The question is, from a structural and thermodynamic standpoint, why does overscreen occur in these ultra-concentrated systems, and how does it challenge the fundamental assumptions of Poisson-Boltzmann statistics? I don't know. I'm not so sure. I think for these, for these to be really, really highly concentrated electrolyte systems, maybe you're talking about stuff like molten salts, or even deep eutectic solvents or something like that, where it's like you just have charged species, you don't have too much solvent, if you will. I think that there may be some assumptions in Poisson-Boltzmann statistics. They use a mean field theory. It is purely mathematical. It's not, I'm also going to say, like, all right, simulations, and it's like, well, there's X-ray scattering, but I think we need to know a little bit more about the situation. Like, in the experiments where they're finding these highly, these situations where there's, like, quote, over-screening, and you have an oscillatory potential profile near the surface. So it's like, okay, instead of the potential just kind of decaying, like, like, just make sure I'm on the right, like, just straight down, it's kind of, it like wiggles a little bit. And that is, the Poisson-Boltzmann distribution is like exponential, basically. And so there's some weird things like, I'm wondering what temperature is happening. I'm wondering if there are other, you're talking about from like a structural thermodynamic standpoint. And I'm kind of wondering, I don't know, it's a lot. I think there's a lot of other things. There's the electrostatics, there's the thermodynamics. You have dipole moments in solvents. So I think there's a lot of questions, and I'm not really 100% sure I know. I also don't know how Poisson-Boltzmann statistics kind of derives itself, and you get these weird overscreening effects. If there's a simulation, I'm kind of like, simulations can be iffy. I'm much more interested in like the experimental data, and I think there needs to be a lot more known. I need to know more about the system itself. I don't know if regular salt and water does this, but I would need to learn more. I would personally need to learn more about it. And your next question is kind of a follow-up, which is to say, a little bit of a follow-up, which is to say, how does the structural crowding at the Helmholtz layer qualitatively alter the concentration dependence of the exchange current density for a simple outer sphere redox reaction, compared to as predicted by standard Butler Volmer theory with Fromkin corrections? So my thought is that I don't know if it's going to make that much of a difference anyway, because the double layer is super thin, and like whenever we do things like signify simulations and stuff, we're assuming for an outer sphere outer sphere electron transfer reaction, the molecule's got to be within 2 nanometers, like 10 to 20 angstroms of the surface, for it to feel the quote field effects and undergo the electron transfer. So I don't know if this Helmholtz layer change, like if it's really this kind of oscillatory behavior. It's like, oh well, the molecule needs to be 5 angstroms, or it has to be 10 angstroms, and then it really like feels the effect, or it actually does a little bit of a push away, and there's another like time element. I've always considered that when you have this tight double layer, it just means the molecule's got to be at the electrode surface to undergo the electron transfer. So for an outer sphere electron transfer reaction, I feel like even if there are some oscillations, we are talking qualitatively, it's like the molecule's got, the molecule is still going to feel a huge force only within a narrow window, a narrow space at the electrode surface to undergo the electron transfer. And when it comes to like measuring the amount of current that ends up getting passed, I'm kind of like, I don't know. I think it's still going to get to the electrode surface, and then it's going to diffuse away, and then you have a diffusion-related issue. Diffusion is going to be the thing that's going to affect the exchange current density. Sorry, I need to know more. I actually need to review more about Fromkin's contributions, but Butler Volmer theory doesn't really tell you anything about like how close the molecule needs to be to the electrode surface. It just gives you a current voltage relationship for kinetics and a rate constant. So it doesn't tell you anything about like how close the molecule has to be for the electron transfer to occur. Mass transport governs all those things. So that's my initial take. There's a lot of things I don't know, but that's my initial take. I think for this kind of structural changes to the Helmholtz layer that give you like a weird oscillatory pattern in the potential profile. I think that there may be other things going on in that kind of system that's going to affect the concentration dependence and the exchange current density and the kinetics and stuff. So that's my take on it. It's a big question. I don't know if you have any further. I don't think it has any further comments or anything like that. But
I don't see any following.
But that's my comments. It's a great question. I would need to know a little bit more about the specific system that gives you this kind of weird potential profile at the electrode surface, to kind of give you, tell you more about why certain things might be happening.
I just want to clarify. It looks like Ron was asking, the peaks represent the reduction in oxidation of electrolyte or LFP cathode. Just to clarify from the previous thing when I was talking about the LFP, it's the LFP cathode. So you could have peaks that correspond to electrolyte stuff. In particular, it happens more with the anode than the cathode, but you can have it like an SEI form, which sometimes will form as a reduction reaction. But when you have a repeatable kind of CV that looks something like this peak right here is LFP goes to Li plus electron plus FP. I'm just shorthand here, the iron phosphate. That is the oxidation reaction. It's this reaction, this charge reaction, the oxidation. And then this bottom one is the opposite. This is reduction. This is lithium plus an electron plus the iron phosphate, FP, goes to LFP. That's what those peaks correspond to. That's what that is. This is the reversible charge-discharge reaction. So the charge is the oxidation, the discharge is the reduction. That's what those peaks correspond to, just to be clear. So there you go. Let's see, where were we? Excuse me. I think another one Ron had here was what, according to me?
Wow. Yeah. Wow. He wants to know
me. What do I think? I mean, I have so many opinions. Should be done to increase the electrochemical stability window for aqueous sodium-ion batteries. Can you? It's aqueous. There may be ways.
Boron-doped diamond or something. I don't know.
I guess, right? Yeah, like the only way to get more volts out of an aqueous system is it's almost like to use a bad electrode, right? It's like to use an electrode that is terrible at either extreme, which is to say it sucks at hydrogen evolution and or oxygen evolution. In which case, it probably isn't very good at anything, which is what like you said, boron doped diamond is great for this. It's a great like substrate because it's like it has like no background stuff at all, and it has a really wide stability window because it doesn't do OR or HR. But as soon as you coat it with something that does, which is like your catalysts presumably, well then your window tightens back up. Like, like if BDD, like, okay, so if you're gonna get stuck with like make up a number, like 1.3 volts, 1.4 volts, and then you start doing oxygen evolution, you can't go higher than that. But you say, I really want to go to 1.8 or something. Well, then you use like a really crappy electrode like boron doped diamond, and you can go to 1.8. But it's like, okay, well, that's my substrate for my electrode, but my electrode is a good electrode, and it catalyzes oxygen evolution reaction also at 1.3. So then I'm back to square one. Like I can't, like the way that the electrochemical stability window is increased for other batteries that are non-aqueous, for instance, are by like, when people are studying non-aqueous batteries like sodium or lithium ion or, non-aqueous ones or whatever. One of the things that people have done is they've used things like ionic liquids. They have no vapor pressure and they have ridiculously wide voltage windows. They're tougher though for other reasons, like they have really high viscosity and the diffusion's pretty poor and the performance isn't always that great. But you can go to like 900,000 volts. So like if that's the trade-off that you're after, that can work. But with aqueous, there certainly could be methods, and like I just don't know in the literature what people are doing. But like in general, it's like it's aqueous. Like you're stuck with what water does when it's exposed to really high or really low voltages, which is that it rips it apart and produces oxygen and hydrogen. So I don't know what more can really be done, to be perfectly honest, other than, like you said, using a really bad catalyst that just doesn't do those reactions very well. And then I don't know how you would accomplish the sodium ion phenomenon if your catalyst is also just bad in general. So it's sort of a fundamental problem, I guess. So yeah, maybe using a substrate that has a wide window like boron doped diamond or something, and getting lucky that your, sodium battery catalyst also doesn't do those reactions. Then you can push the window a little bit or something, I guess. Otherwise, I'm not sure what you could do. Water just doesn't provide the opportunity for high voltages the way, non-aqueous solvents do. So.
Actually, that reminds me, one thing I learned over the last few weeks. So boron doped diamond is actually a semiconductor. I didn't think about it, but like someone was giving a talk, and it's like it's really? Diamond, which is just an insulating material, and then they dope it, with boron, and it's kind of like it's like you have it's like they've removed, like within a carbon lattice or something.
Right.
They removed the carbon.
Some of the carbons.
They put the boron in, and there's
it's a P-type
semiconductor. And I was like, oh, I never thought of it that way.
I guess that makes sense. I mean, I guess that makes sense. It's funny because it's not an intrinsic semiconductor;
Correct.
It's an extrinsic semiconductor. Yeah. But it's not like silicon, which is already a semiconductor, and then you can dope it and just improve its like performance,
yeah.
its conductivity. This is like something that doesn't conduct, and then when you dope it, it will become a semiconductor.
Yeah.
Because usually, like my impression of the doped semiconductors are that they are already kind of semiconductors, and then we dope them to do other things.
Yeah.
This is that's cool. I guess I never really thought about it. We just use it as a substrate.
Yeah, somebody was giving a talk on it, and they mentioned that. I'm like, oh, that's kind of neat. I never thought of it that way.
I guess it makes sense, right? How are you going to get electrons to move unless you give it deficiency and add holes?
Yeah.
Add some boron in there, you get a bunch of holes where electrons can move. So.
Exactly.
Yeah, makes sense. Cool. Yeah, it looks like Zay Cox, you were on the right track trying to help with this. Use the mass of the active material, whatever. I think the point that he was making was that he doesn't know any of that. That's why I was saying you're going to have to guess. Guess a current, figure out where the voltage plateaus happen, and then derive it from there. Obviously, you are correct. If you know the mass of your electrode, or you know some of the materials of it, or whatever, you can get some of those specific values. But I think my impression of the question was that like he doesn't know anything about his catalyst. He just kind of throws a battery together and just like hoping to see what happens. And so yeah, your answer is trial and error. You have to guess currents and see what happens. But I appreciate the contribution there. Ronell, I think.
Yeah, I think so. Ronell Unplugged. Yes, without using Faraday's law directly, derive the mass of copper deposited only from electron balance and prove that it matches the experimental value. I don't know if this is an exam question or not. Because it's certainly not a research question though, because no researcher would make you go through this thing.
To prove something.
Derive the mass of copper without using Faraday's law, and you just know the charge that was passed.
I mean,
for
first of all, if you're saying without Faraday's law
directly,
this might be a semantic argument, but it's like if you're using Faraday's concept, I'm not even really sure, to be honest. This is like necessarily a definitional thing, but I always sort of think of it's Faraday's law of electrolysis. There's a Faraday's law you can look at, if you Google it. Faraday's, if you Google Faraday's law, for instance, it's about like I said, it's a law of induction magnetic field. It's an EMF thing or whatever. I think of Faraday's law generally as just like law of electrolysis, which is just using Faraday's constant to convert charge to moles of electrons. So I don't know if that's like what you mean by like using or not using Faraday's law or whatever, but like to me this just sounds like you have a bunch of current over time, you integrate it or multiply it, whatever the case may be, you get coulombs of charge, and you know the copper equation, like copper 2 plus 2 electrons gives you copper. So for example, for every, you have X, coulombs of charge, which is moles of electrons, and then
divided
it's like
by 2 for each electron.
2 moles divided by 2 moles of electrons per mole of copper.
Yeah.
Multiplied by the
molar mass.
Molar mass of copper divided by its density gives you the
mass.
Like,
that's it.
Or just get
that's how you would do it.
Yeah, like
you need to use Faraday's law to figure out what the mole. You have to convert coulombs to moles.
Is that Faraday's law? Does that mean using Faraday's law? Like I don't. That to me is just stoichiometry. I don't I guess that. Yeah. I'm not sure I can say much more about it. That kind of sounds like what you're talking about doing.
Yeah.
But otherwise, I don't know exactly how to answer this, or if it's like from an exam or it's some other thing.
Yeah, like I could see somebody like asking you to derive to get Faraday's constant by giving you like the mass and the coulombs, and then you have to use the molar weight, and you have to figure out
divide it, and and then you would like back out 96.45 if in theory,
something like that. So not so sure. Anyway, not so sure. Let us know if there's like more to that question, and then we can maybe talk about it. But there's a lot of other questions coming in, so let's get to those.
Yeah, we can move on here. Where are we?
Yeah, it's
a lot of trying to get to
let's see.
Here we go.
What technique is best for evaluating the shift of a QRE over time? Could a long measure of OCB do the job? It's a silver wire QRE leaking into ionic Rayleigh solution by becoming silver chloride 2 ion, I believe. If you're using a QRE, and I'm assuming you're in like a non-aqueous system, yes, you can do an open circuit potential experiment for a long period of time to see whether or not there's any shifting going on. I would add a known redox molecule if you can. I'd add a known redox analyte into your system, because the redox potential of that thing, like if it was ferrocene or something, is known. Like it's not shifting around, it's not changing. So if you know what the ferrocene redox potential is supposed to be, and you notice like, oh, it's shifting, then that's another way to determine. So you could even do a CV, when you start, and then, wait an hour or 2 hours later, do another CV, and then see where the potential, where did that redox CV shift to. That's another way to do it as well. All right, next question.
I'm not really sure this is electrochemistry or exactly how to find the number of lone pairs and covalent carbon bond of NH4.
It's a trick question. There is no carbon in NH4, okay. so there is nothing. There you go.
Zero? Yeah, I'm like, I mean, it's like NH4 plus, like ammonium ion.
Yeah, it's NH4 plus. It doesn't have any lone pairs, and then there's I don't know, looking for a carbon bond. There's no carbon in NH4. This question is it's off.
This is like if bees can think, how many possums fit inside a Ford F-150?
Exactly.
It's like a non sequitur. Yeah. It's like, just like make up a thing. I'm not sure. Yeah, I feel a bit confused. No, I don't know how to build a nuclear. We're not gonna give you nuclear secrets.
Even if we knew it.
Although I did work when I was an undergrad at a company that builds nuclear power plants. It was fascinating. It was cool. I thought it was kind of neat. But that's like energy. That's not, that's not civilizationally ending warfare, which we are not getting into in this live stream. He was just obviously kidding.
Yeah.
But
let's see. There's a question just above that one. Can the ionic conductivity of a solid-state electrolyte be determined from the Bode plot by taking the absolute impedance from a plateau region where the phase shift is 0 degrees? That's a great question.
Yeah, I think so. That is
because that's what we would consider to be the regular solution resistance.
That is the that is a reasonable approach to do that. The tricky thing with this is that you would be making the assumption that the impedance at that point is entirely due to the ionic conductivity of the electrolyte and not due to any other sources, which is not the case. It will be from other sources as well. For instance, the cell cable itself, the clips of the cable, the physical configuration, the arrangement. There's, whatever like physical distance between the sense electrodes in solution there will be like the uncompensated resistance between those two. That will be part of that. So the ways to get around some of those things are to have short cell cable leads, very firm connections, or very few connections. Because, for example, the amount of impedance in ohms of a cell cable and like really good like clips, like if you have alligator clips, or you have like, I don't know, banana cables or whatever you have sort of connecting to your electrodes on either side of your solid state electrolyte or membrane or whatever, if they're very tight and good, you're probably looking at milliohms of impedance, right? So if your ionic, conductivity, the ohms that you're measuring, the absolute impedance at that point is, hundreds to thousands of ohms, like kilo ohms, then great. The milliohms that are in contribution from your cell cables, probably you can neglect it. Great. But if the electrolyte is not very concentrated, or there's a big distance between the sense lines, or there's interference between them or something, and you have a decent amount of uncompensated resistance between the sense lines and your measurement, that could be tens of ohms, hundreds of ohms in some cases. If that number is big, that could convolute your measurement. For example, even in the really nicely controlled conditions, you might have like, let's just say 10 ohms, right? Conservative, like relatively low estimate, 10 ohms. But let's say your, 0 degree impedance measurement is 50 ohms. Well, kind of sucks if 20% of that is, from the uncompensated resistance. So I'm just pointing this out. So, you might have to do like do a test without the solid state electrolyte. Like, for example, if you have like membrane and you have sense electrodes or whatever, right? And you have maybe it's in solution and you have just platinum electrodes or something. Take out the membrane, just the solution. What is the 0 degrees impedance? Let's say it's 10 ohms, whatever, right? And then you put the membrane in and it's sandwiched. Do the same test. Now the impedance is 100 ohms. So it's like, you could just, in this example, you would say, well, my impedance of my membrane is 90, because I'm gonna like, subtract the uncompensated resistance from it manually. It would be that simple. It'd be that arithmetic. So just be aware. That's all I'm saying. Is that the answer to your question is most probably yes. Just be aware of what could also be contributing to that measurement. That's the tricky part. So.
Yeah. Next question. Which of the following arrangement will produce oxygen at anode during electrolysis? Kind of A, B, and C. I don't know if these are also, these may also just be another set of just test questions. Dilute sulfuric acid with copper electrodes, dilute sulfuric acid solution with inert electrodes, fused sodium hydroxide with inert electrodes, dilute potassium chloride with inert electrodes. Well,
if you put the potential high enough, they all probably will. I don't know what to tell you.
Yeah, and
see, again, I'm answering this as a researcher.
Yeah.
This seems like a test question, but my answer to you is if you take any electrodes and any electrolyte and you just ramp the potential up high enough, eventually you will probably produce oxygen.
Right? Fused sodium hydroxide. That's interesting.
I don't know what that is.
All
I'm telling you is if you have an aqueous electrolyte and your potential is really high, you're going to make oxygen. That's the oxygen evolution reaction. Even at a crappy catalyst in a dilute electrolyte, eventually it's going to happen. Yeah. So if the question is actually more a test one that's like, you know, use the equation to solve a thing and prove whatever, and it's academic, pedagogical, something or other, I'm not really sure, right? Yeah. But as a general rule, anything's going to make oxygen if you just push the potential high enough. So
yeah, I might pick dilute sulfuric acid with copper. Like I think that a reaction will occur more easily under those conditions than a lot of the other stuff is inert. But I also don't know what fused.
Well, we sometimes call platinum an inert electrode. Yeah. I don't really like that term so much, but I understand what it's meant by it. So the other possible way to interpret this is that I don't know what fused sodium hydroxide is, but essentially if you're talking about alkaline, the pH goes up. When pH goes up, the standard potential at which something happens goes down. So in other words, the oxygen evolution reaction will happen at a lower effective potential in an alkaline solution. Yeah. So if you're saying for the same, like if I apply 1 volt, just make up a number, and I have an alkaline solution, the oxygen evolution reaction might happen at 0.9 or something. Whereas in an acidic solution, it might happen at 1.4 because it's going to shift with pH. Yeah. So maybe the answer has to do with the fact that alkaline pH goes up, potential goes down, and vice versa.
Yeah, yeah.
So maybe that has to do with it, but I don't know any other context with that question. So we'll sort of move on.
Yeah.
So discussion. Bruh. This dude's got his electrochemistry test tomorrow.
Good luck.
Best of luck.
Yeah.
Wait, tomorrow's Saturday or Sunday, depending on where you are.
Yeah, probably so.
You have an electrochemistry test on a weekend? That's brutal.
Yeah, that's tough.
You should be like having fun. It's the weekend. Oh wait, maybe if you're in graduate school, you're not allowed to have fun. I'm sorry. I didn't mean to say the wrong thing.
Let's see.
Okay. How to study, Suten material says, how to study growth mechanism of a material during sol gel and also during calcination. For example, how a material before calcination was flake transferred to rod gel. Oh, this is a great question. Honest to God, I don't know. But this is something that's like happens all the time. How to study? Well, if you want to say how to study it, it requires some in situ technique, right? You're going to have to get like a, I don't even know. Are there, I mean, I guess there must be like an SEM or an XRD or some kind of spectroscopic
imaging or something like that.
Imaging, yeah, exactly. Yeah. A technique that has like a heated stage or a heated sample where the imaging can occur while you're heating it, so you could observe the morphology changing. Otherwise, my experience from just from grad school and from research is that like this is a thing where it's like I don't know anybody has given good explanations for a lot of this stuff, but it's more like people have done research that it's like you take copper sulfate or something, and if you put it into an oven at 500 C for 3 hours, it makes flakes. If you do it at 700 C, it makes rods. And if you do it at 900 C for 10 hours in nitrogen, it makes, snowflakes and spells out the words great research.
Yeah.
Like these are things that have just been kind of like researched and discovered, and people have just cooked stuff at different temperatures for different times and different environments. And you just find out that kind of stuff. I haven't seen a lot of people, not to say that it hasn't been done or couldn't be done, but I haven't seen almost anybody really ask or think about what you've asked, which is a really good question. Like, how does that happen? Why does it form this shape or morphology? Based on its temperature and calcination or whatever. That's a really cool question. I love this question. I would love to see, a materials science kind of study on, how and why morphological changes occur at what temperatures and what environments. That's cool. I like that. Most of the time I think it's taken for granted and people just say
Oswald ripening, does everything.
Yeah, awesome. Yeah, exactly. Like, oh, hey, I just I cooked carbon for a while and it made this shape, and then I tested it for this application and whatever. That's it.
Yeah.
So that's a cool question.
Yeah,
I love it.
I
love it. So thank you for the question. I really do like that one. And I don't like every question because I'm like old and cranky, and sometimes I hate questions, but I love that question. Speaking of questions, he has another question. It says, how to study the mechanism of sodium ion, lithium ion passes through a solid electrolyte by an electrochemical technique. You're kind of just talking about the diffusion. So the tricky thing here is that when you're talking about sodium or lithium passing through like a membrane and separator or something, I don't know exactly how easily you can decouple that. Like if you have a battery, right? You have a coin cell, you have some kind of pouch cell, whatever. The diffusion that you could measure, for example, at like low frequency impedance measurements, so something like that, or there's something like PIT or GIT, it's called titration techniques, where you basically apply a voltage or a current for a period of time, and then you release the current or voltage and watch the decay at open circuit at OCV. Those are techniques that are used to study diffusion coefficients and diffusional behavior. I don't know that you can pinpoint the diffusion of that kind of test through the membrane compared with just in the electrode structure or in the electrolyte itself. Do you know what I mean? Like, the only way that I can think to do that would be to use something like a blocking electrode. So maybe that's the answer. So like, if what people sometimes do for this sort of a study is so you have an anode and a cathode, but instead of using like carbon or lithium or sodium or whatever, where you're going to intercalate, deintercalate, have diffusion within the catalyst or whatever, you just use like a piece of metal, like steel. Just put steel on both sides. It can't intercalate. It can't do any redox. It can't do anything. So what you're doing is that when you start trying to polarize or do any kind of electrochemistry, you create a field by doing electrochemistry between the two sides. Even if they're identical, you can create an electric field by using a potentiostat. And what that does is only move ions in solution, basically. And so there's no intercalation, there's no deintercalation, there's no redox basically happening. There's double layer and stuff, but there's no real redox. And so then what you can do is you can say that the diffusional information I get from impedance in particular is a good one to do, is the transport through the membrane. So blocking conditions, you can like do a literature search for like blocking conditions, blocking boundary, these sort of terms. That sometimes is used to study the transport properties in the electrolyte or of the membranes or separators or things. That might be the way to accomplish that, I think. So give that a shot. I did a webinar some time ago on a researcher that did this kind of a test to study what's called the tortuosity of a membrane by doing impedance and blocking conditions. So it's not exactly it's similar to what you're talking about. I mean, it's the path through which an ion maybe passes through. How winding is the path of a thing of an ion passing through a membrane. So that's one aspect of what you've asked. It depends what you're looking for. You're looking for tortuosity, porosity, diffusion coefficient. What are you specifically looking for? But blocking conditions will be a way to do that because you take out the effect of the redox reactions that might occur, because otherwise it's hard to pinpoint exactly the membrane, for instance, if you have a lot of other stuff going on.
All right, next question. When calculating charge in a redox peak, you get the area under the peak's curve and subtract CDL, the capacitance. But when do you start and end the peak? Is there a threshold, or is it usually subjective? I think what he's referring to, let me just share.
Charge in redox peak.
I just did let's see, make a new slide. I think if you're looking at the charge in like CV, we're talking about doing
Like the current time.
Yeah, so sometimes it looks, so if you have time, you have current, I've seen these, but I'm not like great at them. And I kind of can look like this. Sometimes I look like this.
Zach, that's great.
Oh, actually good.
I was just messing with your slides earlier today, you know, for geometry stuff. That is spot on.
Yeah. So yeah, you want to get the amount of charge, and you know, so maybe if this is like, I don't know, if this is 0 or something, it's like this is a double layer. But then yeah, if the current is positive or negative, then I've always found that to be kind of a good like indicator, if you will, of like what's, because even here there are Faradaic charges happening, like in your CV, you know, and let's say this is what your CV looks like. You know, so let me get it one more time to exaggerate a little bit, but then because even like, yeah, the peak is here, right? This is your peak. But even here, like in this region, there is still like oxidation occurring. There's still redox events occurring even in this region. Actually, this whole region is still oxidation, you know, even though the potential switching. So it's really only when the current goes down into this direction that, you know, you're actually getting charge associated with the opposite reaction. So yeah, so that's why I would, you know, there's the peak current, which is a single value here, but then area under the curve, you know, that's this whole thing. And then, you know, if this is 0, you may say like, okay, this is my double layer, so I want to not have that as part of the, you know, as the thing, and then I just want this, you know, I just want this yellow area. So that's something that you would have to determine. But just remember, like, if the current is positive or negative, that's a really big indicator as to what's happening, you know, what reaction is actually occurring.
Yeah.
Okay. All right. We have a few more minutes.
I know. I know. Is your voice going to hold up?
Voice is doing okay. It's the morning when I'm a phlegm pinata, and I'm just chugging Ricolas like it's going out of fashion.
It is going out of fashion, but not with me. But yeah, no, I think we'll avoid our 7 a.m. live stream. That would be good. So in Pine -100, I don't know what -100 means, but in Aftermath Blue, when performing CSCP for a GCD alternative, the time axis unit is an hour and measures too much time, measures 2 hour, well, just 150 seconds pass, and curves look similar. Okay, I can explain what's happening, 369 Omniverse. If you're using CSCP as an alternative, so this depends on the version of Aftermath you're using too. Okay, so apologies to anyone else. This is like specific to Pine's software and how it works. So don't worry if you're not using our software. This isn't how every software works. So there was a time where the way Aftermath worked was in a CSCP, you can put a trigger. So it's basically GCD, right? But we have battery techniques now. We have GCD you can do. Please contact us if you want battery methods. I can give you a license file for battery methods. We actually have like real GCD battery methods. 369 Omniverse. Just email us.
I'm just putting the pine wire.
Yeah, pine wire.
We'll also need to update firmware. If you have maybe you have a WaveDriver 100, possibly. Maybe that's what the 100 is.
Maybe that's what you mean. WaveDriver 100. Yeah. I can give you for free. I could give you firmware update. I just need the serial number of your instrument. I can give you firmware, software, permissions files. I can give you everything. It's totally free. That you won't have to run into this problem. But to answer your question, the way that it used to work was you would set, for example, the charge and the discharge for CSCP, right? And you'd say apply, 1 milliamp, whatever, for 2 hours. Maybe you weren't sure how long it should take, right? And then you do minus 1 milliamp for 2 hours, but it only took, like you said, 150 seconds until it hit the trigger, and then it turned around. What Aftermath used to do at one point in time, we fixed it. It's been fixed, but again, you're probably just using an earlier version, was that our Aftermath artificial, when it hit the trigger at 150 seconds, is Aftermath artificially, inside Aftermath, not to you, says, I hit the trigger, that step is over, go to the next step. And the way that it does that is it says 2 hours have gone. Now, obviously 2 hours haven't gone, but what it does is it changes the time axis to 2 hours because it pretends that that step completed the time limit. Now that's annoying because when you're watching it live, 10 seconds went by, but it looks like 2 hours went by and it didn't. And so the next step, if the 2 hours actually completed, would have started at 2 hours and then 4 hours and 6 hours. And so you have a tiny sliver of data, tiny sliver of data, tiny sliver of data. And what you really want is just those things actual time, 150 seconds, 300 seconds, 450 seconds. Okay. Now that's what a proper GCD would do. And we fixed Aftermath at one point in time, even if live while you're running, it looks strange. When the experiment finishes, it should correct the plot and cut out that dead time, that extra time. But because CSCP was not originally designed for battery GCD tests, that's how it was kludged to work until we got battery methods, which we have. Again, I can give you the license. You just don't have a license file for it. You probably just need to write to unlock the license file for it. Because the real GCD test, you shouldn't have to enter time at all. You just say, I want 1 milliamp until I hit 4 volts or whatever, right? And then however long it takes is how long it takes. That's what a GCD test is. And so that's what we have. We have those tests where you don't have to put how much time. And if you do put 2 hours, that's fine. If it doesn't last 2 hours, you don't get that kind of time splicing thing. But that's what's happening. So apologies for that, but please contact us. I can set you up with the proper, experiment technique so you can do a real battery test if you want. But that's what it used to do before we implemented the battery method. So. Let's see. How much more you got in you?
I'm okay. You're doing most of the talking, which is very helpful.
I'm trying to take the brunt of it here.
And you are.
Okay.
We only have maybe about 10 minutes ish left.
10 minutes, yeah.
Someone
was asking about
balancing redox reactions, but
I mean, this is. Yeah, I don't know.
I think we need
balancing. Well, it's do you have a specific reaction you need to balancing redox reaction? This is sort of an important thing you learn in either high school or undergraduate chemistry class. Usually, it's just stoichiometry. And if you're talking about balancing redox reactions, it's the same kind of philosophy. You're just adding electrons and charge into it, so you have to have the same amount of charge. So when you do stoichiometry, it's you're balancing the number of carbons and hydrogens and molecules on the left and on the right, and you're just making sure you have the right number of atoms of elements on the left and the right. That's stoichiometry, right? And when you have redox reactions, you just have to make sure that the total number of charge is the same on the left and the right. So without doing too many specific examples here, I guess, and just, I don't know, going through the probably boring exercise for a lot of people, I suppose. It's like if I have +4 total charge on the left, I just got to make sure I have +4, +4 total charge on the right, or -4 plus, whatever. It's just making sure that the numbers line up on the left and the right side for charge, in addition to
number of atoms,
the elements. Yeah, exactly. So you can't have more hydrogens on the left than on the right. You can't have more pluses or minuses on the left and the right. That's all. I don't know how much more we really want to dig into that. It's a bit of a academic exercise, I think, for like a chemistry class, maybe, perhaps not exactly for now, but explain about
EMF.
Explain about EMF when electrode changes polarity. But it's kind of like talking about the same thing. It's just EMF is just potential, and polarity is just changing potential.
And one thing to at least keep in mind is, so it's like, when we polarize an electrode like positively or negatively, it's always with respect to a reference electrode. So you can always have like, it might be a positive potential, but there may be like negative charge on the electrode because the reference electrode is like way more positive or way more negative. So the electric field, it's literally just kind of, I think of it as the double layer. And you're, because we model the double layer as a capacitor, the potential of the working electrode is that capacitance value with respect to a reference electrode. So it's this voltage versus a reference electrode. And so you're building up charge, and there's a decay. And actually, we just talked earlier about, kind of the Helmholtz distribution and Poisson-Boltzmann distribution of electric charge and stuff. So I guess I have to think like, we always draw that. I don't know how deep do we want to go into?
You could talk about potential for the next like 3.5 hours if you want.
Talk about potential. Maybe I'll share. Let me get this one. Let me get this one slide that might help give a good visualization, sort of say. All right, so I'm gonna share. Let me share this screen.
Sharing is caring.
Sharing is caring. So this is it's my favorite equation, but basically, one way that we kind of look at or think about the electrical double layer is the difference between the potential of the metal and the potential of the solution. And in reality, we kind of have this kind of drop off, right? We build up charge on the metal, and we build up, and there's a buildup of charge in the solution that kind of balances itself out. And so as we change this phi m, phi s kind of remains the same, right? Phi s is just the solution potential. Phi m is something that we can kind of adjust with a potentiostat. We can bring it, more down. We can bring it more up. And kind of one thing I, at least in my lecture about this topic, which I think I talk about it here. There are kind of these three things. There's the electrochemical potential. There's this picture of phi m and phi s, the solution potential and metal potential. And then the drop off, that's the kind of EMF field. As you adjust the potential, you're changing the phi m. And then there's the microscopic picture, which is the Helmholtz layer, inner Helmholtz, outer Helmholtz, all that kind of stuff. So as you're changing the polarity of the electrode, you are changing this phi m, you're moving this up and down, you're changing the amount of charge on the electrode. And when you switch polarity, I don't really... The thing that can be very confusing is that you have a reference electrode. So what you actually measure oftentimes is really like phi m minus phi s minus a separate like reference electrode and solution potential. So it's always kind of hard to say like, oh, when the electrode changes polarity, what happens? It's like, well, what does that mean? Because it could change polarity without this part actually adjusting all that much. So that's where it gets a little bit confusing. But I do encourage you to use this as a good conceptual framework for what happens when you change the potential of your electrode and what's happening. All right.
Rahan says, during CO2 reduction, my peak coincides with HER peak in alkaline media. How can I identify my peak from CV or LSV? I have two thoughts. One is to change and adjust the scan rate. I think possibly doing slower. Is that what you think about, doing slower scan rate? If they're close, something like that. Maybe if you scan really, really slowly, you might be able to like resolve the CO2 peak before the HER starts. If you scan like really, really slow, like, I don't know, like 1 millivolt per second or something. The other is possibly try a pulse technique. Maybe it'll help clarify a couple of peaks. You'll have to probably play with the parameters, like the amplitude and the, period and all those kinds of things. But possibly you might be able to like have a sort of a background, Faradaic subtraction of one part of it, and you might get to resolve two peaks that way. I can't really think of any other suggestions though, other than scan rate manipulation and pulse techniques.
Yeah, it's very
right.
That's one of the big problems is like CO2 reduction also coincides with hydrogen evolution reaction, not just in alkaline media, but with many media. So it's a pain. Non-aqueous systems are the only ones that really allow you to like resolve those two things. But
yeah. Okay. Well, anyway, what I suggested might not work if it's a fundamental problem, but I don't know. You could try playing with the parameters of your techniques and see if it helps. Yeah. Let's see. I'm not sure if I answered the peaks correspond to the electrode. Electrode. I can't remember if I like covered this already. If this is just a follow up. The peaks correspond to electrode reduction and oxidation. And how do we see the voltage at which HER OER occurs in CV for sodium ion aqueous systems?
Why do we consider the peaks in CV to correspond to HER OER occurring voltages?
Well, first of all, OER and HER don't always make peaks.
Yeah, that's right.
Those are definitionally like the stability limits of water as a solvent, right? Oxygen evolution occurs at the extreme upper potential window of water where oxygen starts to be evolved. And we talked about this like either last time we did a live stream or the time before. Like someone was asking about peaks and the what's happening at the electrode surface. We kind of delved into this in one of our live streams, and it was like you did a really like thorough job talking about like you have the double layer and you have the surface in this condition, and then it was like, well, when you have HER, that doesn't happen.
Yeah,
it's like the whole thing, because it's like now it's like gas is getting evolved and you don't have the situation of like the situation is just different. So you don't get a peak at all. The current just keeps going up or down, whichever direction. So you don't always even get a peak, first of all. And then I don't even know exactly how to answer. So you're talking about like there's an electrode reduction reaction that occurs at some potential. You have peaks like I drew for the LFP earlier. I don't know if that, like if you're talking about something different, obviously LFP isn't aqueous. So we're sort of talking about different things, but those are reactions that are happening of the electrode, doing some redox reaction. Then if you keep pushing the potential farther and farther away, eventually you're going to do OER and HER.
Yeah, and it might not be a peak.
But those are separate.
Yeah,
there might not be a peak. They might just
go
current
up.
might just shoot up or down forever. Yeah. So I don't know. Those are kind of different things.
Mm-hmm.
Alex, Alex just to be clear, that's not you. Says, what redox couple can you advise to replace ferrocyanide? In general, my answer is ruthenium hexamine, but you say you're working on an optical technique to see diffusion layer via refractive index changes in the electrolyte. I don't know if Ruhex has any optical considerations, but as a general rule, ferrocyanide annoying and terrible. It forms Prussian blue, it sticks to stuff, it doesn't always behave well. Ruthenium hexamine is wonderful and behaves quite nicely. But I don't know about the optical side of it, if it does anything or doesn't do anything. I don't know.
Yeah, I'm thinking about this because like you could use a molecule like methylbiologen, and that is very soluble in aqueous systems, fairly inexpensive, and it turns like blue if so it won't be a refractive index change where you can see things. It'll be like it'll be let's see, so but you're looking for an optical refractive index change in the electrolyte. So to a degree, I'm thinking it's just like, okay, working in optical to see the diffusion layer via refractive index change in the electrolyte.
So you need a simple redox pair that also does some kind of optical thing.
Yeah. So right. Maybe if that's the case, like methylbiologen. That could be a thing that works well.
Yeah, I don't think ruthenium hexamine changes any optical properties when it goes.
Or it would be in like the UV or something like that. I don't know if it does either, at least easily.
Yeah. I'm not sure there's been many spectroscopic studies on Ruhex.
Yeah.
Could be, but I don't know.
Yeah.
It looks like Ron's question was more about onset voltage. So he meant to say, how do we know that it's starting? There's two answers. One of them is that it's entirely subjective, which sucks because, how are you supposed to know? Good question.
It looks like it's going up. It just looks like it from the scale.
It kind of looks like it's flat, and then it's now it's not. So there. Okay. Well, yeah.
Or it's like this. So it's like, well, yeah.
So there is a lot of subjectivity. Yeah. The only kind of other mathematical way you could do is you could look at either the first and or second derivative of the data. So remember from calculus that the derivative of a plot is the slope of that plot. So you could, it's still arbitrary, there's still subjectivity here, but you could make some consistent rules for yourself, for instance, that when the slope is something, right? When the slope is at least some value, that is when I determine the onset potential has occurred. Or the second derivative. The second derivative is concavity. So it could be that it's like flat and then it starts to go down. That would be like concave down. When the second derivative goes negative, that's the onset potential. That could be something, but maybe it's already negative. Like there's ways you could justify this mathematically, algorithmically, but those are also subjective. So unfortunately, there's no right answer to this question. You will have subjectivity. If you want to get kind of nice and technical and try to use some derivatives or mathematical algorithmic, it might be nice, but there isn't really a right answer, unfortunately. I think people have to sort of, a lot of times, just say, that's about the onset potential, it's tricky, which is why I think also a lot of the metrics tend to be like potential at 10 millionth per centimeter squared, something like that. Because then it's like, that's a current or a current density that's obtained. And it doesn't matter where it started, it matters where you get that current. So that's why some people use those metrics, because it doesn't require someone to say, hey, my onset potential was 50 millivolts better than yours. And it's like, oh, well, mine was better if I just assume it started here. You could just make it up and say yours is better. It's like, it's not ideal. It's too much subjectivity. So I think we're going to have to call it here. There's a few other questions here, and we do appreciate everybody, but we've gone a little over time, and Alex has to probably go to sleep for the next 16 hours. So,
I wish.
Yeah. I think we'll be here next week.
think so. Maybe. I hope I'm alive then.
Assuming you're well.
Assuming I'm well.
I mean, if you have to be home, you know, we can still do it remotely.
Yeah. That's also true.
I will be here for most of August. Okay. You will be.
I will be here less of August. Ish.
Yes, and I will be less of September. It's possible we could do these solo, but I hate doing it solo.
I think most of the Fridays in August, I am not in the middle of something. But the rest of the week, I'll be in the middle of something. But like Fridays, I think I should be around. July was when it was like, now I'm just out all the time.
It's one of those things.
Yeah.
At some point, we will be back.
Yeah.
Together. Ron, it's not that simple. It depends what you're talking about. If you're talking about the OER and the HER, it is the electrolyte. It's not the electrode. Most of the time, it's not the electrode. It's not the electrolyte either. It's the analyte. It's the material. It's the compound you're reacting. The electrode is not often the thing that's reacting. The peak isn't usually the electrode. It's if you have a redox reaction, it's a molecule in solution. That's reacting. That's doing a thing. That's what's reacting. But it depends. It's the electrolyte. It's probably not the electrode itself reacting. Just to be clear. But it depends on your system. So as you spam to get us to answer the last question, I get it. I understand you're talking about it. We should be here next week. If you want to ask some more questions, Ron, please join us. And then we'll try to find dates here and there. Even when I'm abroad, possibly we can find some fun time to do it remotely. Maybe not. Maybe we'll see.
Yeah.
I'll be like 1,000 hours ahead of you. We'll see. All right. Well, anyway, thank you, everybody. We appreciate everybody joining us through this bizarre time where we're
just traveling out of it and all that stuff.
Yeah, and Alex is half dead, but that means he's half alive.
I'm Schrodinger's Alex.
Schrodinger's Alex. That's right. At any moment in time, you're as alive as you are dead. Right. Okay. Well, the next time we are both alive and both able to do this live stream, it's probably next Friday. Famous last words. We will see everybody then. Until then, I hope everybody has a great rest of your weekend, and see everybody next time.
Bye.
Bye.